So like we were covering yesterday, I said that anytime you're looking at an acid-base reaction, it's the best idea to take a look at the conjugate base for each proton that you're looking at, right? So in the example of HA, we could pluck off that proton from A, transfer it to B, and then we want to look at the stability of that conjugate base. We had that big list of rules where we had atom first, resonance second, induction third, and then orbital last. These rules are pretty important, and they're really good guidelines for predicting relative acidity. What we're going to do today is kind of a play on that. Whoop, wrong one. Where I'll draw a molecule for you guys, and I want you guys to predict which proton on the molecule will be the most acidic. So let's come up with a little bit of a guideline system. When in doubt, draw all possible conjugate bases and compare their stabilities. We'll do an example first. So let's do this one. Identify the most acidic proton. And we'll do this example. I'm going to do a carbon, double bond carbon, single bond carbon, and on this carbon, we'll have some nice red protons. And up here, we'll have a blue proton. And over here, I'm just going to put generic R groups, meaning we've got some other stuff dangling off of this molecule. If we think about those red protons, they're all equivalent, right? They're spinning around in space like an umbrella. But they are different than that blue proton. So now the question is, which proton is going to be more acidic? One of the red ones or the blue one? So I'll give you guys a minute to think about that and then discuss with your partner and see if you guys agree. Which symbol?
The dash to the hydrogen, the proton.
That's a good question. So the question was, what does that symbol mean when I do bracket around a proton? That just means loss of a proton. So minus H plus is minus loss of a proton. So I'm going to draw out all of our possible conjugate bases. All right, give me a thumbs up if you and your partner have a consensus on which of the two is more acidic. A few people? Put a thumbs down if you guys don't agree or don't know. All right, we've got a fair number of people not voting here. All right, well, let's take a look at this, right? So let's think about that blue proton. If I pluck off that blue proton, I could argue, hey, that blue proton's in an sp2 lobe, right? The red protons are in an sp3 lobe. I know that that orbital rule states that protons coming off of sp2 lobes are going to be more acidic than that sp lobe. Seems reasonable, right? Does anybody have a counterpoint to that?
The middle carbon can go less than that.
So you're saying the blue proton, if we pluck that off, can have resonance? Or the red one? You don't know anymore? That's a good question. So let's think about this one. Is there any resonance if we remove that blue proton? No, we can't move that negative charge around without violating an octet rule. However, if we look at this top one, what can we do?
You can resonate that double bond.
Ah, yes, this negative charge we can move over, and we could transfer that lone pair over here. So we could say, all right, if we do this, there's actually a resonance structure where that proton can move around, or sorry, that negative charge can move around, and it can reside over on the right carbon. So let's draw both resonance structures. All right, so now the question again is, which one's going to be the more acidic proton, red or blue? What trumps the other? Is resonance more important, or is the orbital hybridization more important? Resonance, right? So if we look at this, that must mean that these ones are more acidic. Because resonance, stabilized conjugate base, is more important than hybridization. Sorry, let me scroll up for you guys. There we go. So we're going to be doing a fair amount of this today, trying to look at a molecule, look at all the protons on that molecule, and then predict which proton is going to be the most acidic. I'll give you guys some examples, but I want you guys to use some teamwork on this, and so talk it out with your partner, and then we'll come back together as a class to decide. And I'll give you guys 3 different sets of protons to choose from. All right, the first example, I've got an oxygen here. I've got a red proton. I've got 2 blue protons. And I've got 3 green protons. Goal is to pick which one of those is going to be the most acidic. One of the blue ones, one of the green ones, or the red one. I'll keep on drawing other ones over here. Here's example 2. Whoops. And then I'll do a third example over here as well. Let me move these. And each of these nitrogens has a lone pair. All right, so let's try to figure out which protons are most acidic for each of these 3 examples.
also has it's SP2 as opposed to SP3. So I would say
This one, did you get this one?
this well, I don't see for this one. I'm showing you the electronegativity carbon.
Nitrogen needs carbon to get rid of it.
Yeah, but there's a big thing with because you can create a lot of
All right, let's check in on the first one, the one on the far left. Thumbs up if you guys are agreeing on the most acidic proton in that molecule. Please vote. Come on, guys. There we go.
This is why democracy fails.
All right. So, does anybody, how about in the middle section right here, does anybody have a hypothesis for which proton is going to be the most acidic?
We assume the red one,
You guys assumed the red one? Why do you think that?
because of oxygen being have the charge.
Yeah. So he's saying this red proton because the resulting conjugate base would have a negative on an electronegative atom. First priority rule is look at the atom that that proton's attached to. If it's electronegative, that's usually going to be the most acidic proton, right? So protons coming off of oxygen usually are going to be fairly acidic, right? Because that oxygen's happy with that negative charge. All right, if we pulled one of those blue protons off or a green proton off, we'd have a carbon with a negative charge. Not super happy, right? Carbon's not very electronegative. All right, what about the middle one? Thumbs up if you agreed with your partner on this one. Couple people? All right. Well, if we go down that list, right, most important is atom, right? If we pull off a red proton, we've got a negative charge on a carbon. If we pull off that blue proton, we've got a negative charge on a carbon. And if we pull off a green proton, we've got a negative charge on a carbon. So we're at a tie, right? Next most important rule, resonance. If we pull off a red proton, are there any resonance structures that we could draw where we could delocalize a negative charge?
The double bond.
Let's try it. Just for the sake of argument, I'm going to say, all right, I've got a negative charge here. Can I delocalize this negative charge that way? Not really. Not without violating the octet rule. I mean, what you could do is you could, I guess, delocalize it up there. So maybe we'll put that as like a question mark. I'm going to redraw these in. All right, what about the blue one? If we deprotonate the blue one, will it have any resonance structures?
yeah, nitrogen.
So if we try to form a triple bond with nitrogen by deprotonating that blue one, we'd violate the octet on that nitrogen. So the blue one's probably a no-go. All right, what about the green one? What do you guys think? If we deprotonate one of these and we say, all right, what if we now have a negative charge here? Is there any way to delocalize this?
Yeah, the charge could go to a double bond to the one to the left of it.
So
Then
you-
that double bond could become a lone pair.
All right, so if you do that, then the nitrogen has a negative charge on it, right? All right, so we've got a couple of options, right? We've got two resonance structures. We could deprotonate the red one and delocalize that negative charge across two carbons. Or we could deprotonate one of those green protons and we could delocalize that negative charge between a carbon and a nitrogen. Which one do you think is going to be a happier resonance structure? Yeah, the green one where we delocalize to that nitrogen. Simply because that nitrogen has a negative charge. So this is one of those more nuanced examples where even if you have resonance between both of them, you've got to compare the two resonance structures. So let's make a note here. resulting conjugate base has negative that is delocalized via resonance across a carbon and nitrogen. So that one was a little tricky, but like I said, if you're ever in doubt, try to draw out all the conjugate bases. If there's resonance structures, draw every resonance structure and then compare the stability of each conjugate base. All right, let me clean this up a little, just so we're comparing our original structures. What about that last one? Thumbs up if you agreed with your partner on it.
No, we didn't get
Thumbs down if you didn't. A few thumbs up, a few non-committal votes. All right, let's look at this one. If we pull off that green proton, we would have a negative charge on nitrogen. If we pull off the red proton, we'll have a negative charge on carbon. And if we pull off that blue proton, we'd have a negative charge on carbon. Most important rule? Yeah, the atom itself, right? So even though if we pull off some of the other protons, we might have resonance, doesn't matter. Atom's the most important rule. So in this case, we would say, all right, this green one is most important. Most electronegative atom. All right, is this starting to make more sense? Let's do a challenge one. I like challenges.
we get more time for this one. Though?
Yeah, I'll give you guys more time for this one. All right, this one's a fused ring system, so two hexagons that are fused together. We've got a methyl group sticking off here, so that's a CH3. CH3. What's this functional group called with the oxygen? Ketone, right? It's got a carbon on both sides. It's important to remember functional groups. Then over here, I'll draw in a double bond and a single bond. If you're a little rusty with bond line structure, it might be a good idea to draw in some of those protons too.
So what, is the ring on the left straight across the bottom, or is that a carbon that's...
Sorry, this is a carbon right here. Is that what you were asking?
Yeah, I just couldn't tell if it was a five-sided or a six-sided.
Yeah, let me angle this a bit more. Oh. There we go. More artistic. We'll draw in those lone pairs for completion's sake.
where it's pulling electronic,
Kick down.
closest to the electronic, to the electronic.
Oh, okay, so it's the floor.
Yeah, it's
Yeah,
pulling
it's just,
No. It's working on ring system, so I'm gonna say. It may not be a Benson, but it's working on ring system, so I really doubt it's gonna come. We're wrong sometimes.
I'm disregarding the whole set.
No, I don't know if it is.
I can't.
it's only, it's not the other one, so that doesn't. Right.
I don't like the idea of taking one from the ring system, but I think you might be right. Because it's not a Benson.
Oh, yeah.
So you take the double bond
Take that off.
and the negative charge here. Without pressing the on test on the card.
Yeah, but resin.
You just put a double bond.
Yeah.
Where do you get resonance?
Would become basically a lone pair, which,
Yeah.
Maybe a positive.
but the
I'll
should
tell
be
you.
Then draw.
That's what I was saying.
but not a dotted line.
You just said it better,
Just
so.
a dotted line that I'm towards.
Or here you
I'm not towards the opposite.
Oh, right.
Because you're pulling up a lone pair to make it negative.
But still,
Argue about
still
it.
two.
We would never do this. The other option is that this.
Yeah, still two rail.
But I feel like
Also delta negative.
Right.
Raise your hand if you feel pretty confident about this. Raise your hand if you want a little hint.
Maybe a little.
Little hint? All right, I'll give you guys a little hint. First thing we want to do is try to narrow down our protons, right? We've got a ton of protons on this molecule. Some are not going to be very acidic. Which protons do you think are not going to be very acidic?
Single bonded carbon.
Yeah, things coming off of sp3 hybridized carbons, for example. We know those are probably not going to be very acidic. So, for example, if we think about this CH3 group, those protons probably not going to be very acidic. Same thing with this CH3 group, or this CH3 group, or here. So we can go through and we can say, all right, those probably aren't going to be super duper likely. But let's go through and list some other ones. And so I'll draw these in. I've got some red protons here. All right, I've got a blue proton here. Maybe that's it. Or maybe I've got a green proton here. Or I got to get a new color here.
There is no green.
There we go. We'll do green, and then we'll go back to purple here. All right, so if we're thinking about this,
Oh, the green one shouldn't exist.
the green one shouldn't exist.
That's right.
What's wrong with the green one if I draw that in? Texas carbon. That's a really, really common mistake that people make is they say, oh, what about that proton? Doesn't exist. Always double check. I put it in there to check you guys, yeah. All right. I've got a good sense of humor, don't I? Good joke. All right, now let's take a look at the red, blue, and purple. What if we pluck off a red proton, right? So I'll do this one down here. I'll say minus H plus, and I'll put this H plus in bracket. If we think about this, we've got a lone pair now. It's on a carbon, but the negative charge would be on the carbon if we pulled the red proton off, the blue proton off, or the purple proton off. So we're at a tie, right? What can we do with that lone pair, though? Resonance. So we could say, all right, with this one, we can put that lone pair here, move that pi bond up, so that works. There's some resonance there. What about that blue one? If we pull off the blue proton, will that have any resonance?
Yeah. They're the same.
Let's try it. So if we do that, I'll do minus H plus. If we do that, now we've got a negative charge here. Can I delocalize it this direction? No, not without violating an octet rule. Can I delocalize it this direction? Okay, let's try that, and then we'll move this up. Okay, so let's draw our new resonance structure that we get out. So now we've got double, double, whoops, this should be a single. Does this look like a very happy molecule?
It needs the, it needs the,
There's some ring strangle.
It's gonna wanna be
it needs the lone pairs.
Yeah, so let's take a look at this resonance structure. A lot of students are tempted to draw this. However, if we look at this carbon right here in red, what's its hybridization? SP, right? So this red carbon would be SP. What angle do SP atoms like to be at? 180. Does this look like it's a very happy 180 degree angle? No. So we'll just put a frowny face.
So is that ring strength? Is that what it is?
Exactly. So SP hybridized atoms really want to be 180. You're not going to pull them that far out of that 180 degree angle, or 180 degree angle. So this one's probably not a very likely resonance structure, but that's okay. We're just trying to do a bunch of possibilities. All right, our last one is the purple one. So I'll do minus H plus. We'll draw it over here. All right, now we've got a lone pair right there. Can we do anything special with that?
Yeah, you can share the negative charge with that other carbon that's on the other side of the double bond, right?
Okay, so let's try to delocalize it. We'll say, all right, let's move this down here. We could move that pi bond over there. I agree. I think that's a good idea. I need more space. Here we go. All right, so now we can show that negative charge delocalizing to that carbon. But we have a double bond here now. Let me put it on the inside of the ring. Are we done? Yeah, we can delocalize this even further, and we can say, all right, this can go here. We can move that pi bond up. All right, and let's draw this last resonance structure. Do we all agree on those three resonance structures? All right, so now I'm going to zoom out a little bit just so we can see everything. We're comparing all three of these conjugate bases. Which one do you think is going to be most stable?
Red or purple?
Well, we did say the red one, if we remove that red proton, has resonance. But the purple one can delocalize across three atoms.
But doesn't the oxygen want more electronegativity, so it prefer not to be delocalized as much?
In this case, more delocalization is better. Because both of them have a negative charge on oxygen. This one has a greater distribution of electron density over more atoms. That's going to be more stable. So this will be the most stable conjugate base because it has the most delocalization. Does that make sense? It can be a little confusing, especially when you have to draw them all out. It can be time consuming, I understand. But with this one, for example, if we draw it all out, we can, but there's only really two resonance structures, which is great, but it's not nearly as good as three resonance structures. Three resonance structures kind of takes the cake in this example. Make sense? Your problem of the day is asking you to do something similar. I gave you guys a challenge problem. It's up to you guys to look at the protons that exist on that molecule and then decide which protons are going to be the most acidic. It might take a few tries of plucking off protons, drawing out a bunch of conjugate bases, but it's really good practice to go through all of this. Does that make sense? All right. Let's go on to the next topic. Next topic's choosing an appropriate base, right? So now we know how to identify the most acidic proton. But if you're in a lab setting, you want to choose the best base for that proton, right? So did everybody get a handout up front? If you guys don't have one, you can run up really quick and grab it. We're going to use it today. All right, so let's go back to just the basics, and then we'll take a look at this handout that I gave you. If we've got HA, and we've got our base B in solution, we know we've got an equilibrium reaction where we've got our conjugate base and our conjugate acid. And we said that essentially we have two acids in equilibrium, right? We've got our original acid, and we've got our conjugate acid. If we really want to deprotonate A, we have to be aware of the conjugate acid and how acidic the conjugate acid is. So let's kind of rephrase that a little bit. For the deprotonation of HA to be favored, it must have a lower pKa than HB plus. Right? We talked about the equilibrium position yesterday. We said the stronger acid will push the equilibrium to the opposite side. So in this case, we want HA to have a low or lower pKa. And we want this one to have a higher pKa so that this reaction gets pushed to the right. All right, so let's take an example. First example I have is acetylene. That's a carbon-carbon triple bond. And I'm going to have some base. I'm going to just write in a generic one. We know our conjugate base is going to be acetylide with a negative charge. And our conjugate acid will be HB plus. I'll give you guys a little bit of information. If you go to the pKa table, this acetylene has a pKa of 24. What does that mean about HB? What pKa should it be if we want to deprotonate acetylene? Yeah, larger than 24. Must be greater than 24. So let's take some examples. Let's say I've got acetylene and I'm going to use hydroxide. We know hydroxide from Gen Chem is a pretty good base. If we think about this equilibrium, we'll have our acetylide ion. What will our conjugate acid be? H2O, right? Hydroxide, when it seals a proton, forms water. So if we think about this, okay, we've got a pKa that's equal to 24. Does anybody remember the pKa of water? 15 about. So we'll say pKa of 15. Is hydroxide a good base? No. It's one of those things where we're taught in Gen Chem that hydroxide's a great base. Not always. In this case, it's a poor base. So Let's make a little note of this. Not a good enough base. Simply because this pKa is now lower than 24, not larger than 24. All right, so what we need to do is take a look at our common bases handout and say, well, we've got to pick a better base. Let's go down here. We need a base where its conjugate acid is above 24. So again, if I go through, I could say sodium bicarbonate, conjugate acid of that base is 3.6. That's not going to work. Pyridine, next one down, 5.2. That won't work. All right, potassium carbonate, that won't work. Triethylamine, that won't work. Sodium hydroxide, that won't work. Potassium tert-butoxide, that won't work. All right, we're out of our weak bases. We've got to pull out the big guns. Sodium hydride, 36. Will that work?
Yeah.
Yeah. So we'll say, all right, let's try sodium hydride in there. It's probably a better base to use, and we'll plug that in.
Are they to be provided on quizzes, or we just bring it, or will we not need these?
If you need certain pKa values, I will give them to you. I don't expect you to memorize pKa values. So sodium hydride's a little bit weird, right? Sodium is a metal, hydrogen's a nonmetal, so this is ionic. We've got an equilibrium. We've got our acetylide ion. And what's our conjugate acid? If H minus steals an H plus, what do you form? H2, which is a gas, liquid, solid? Gas. So this is actually a cool reaction. When you throw these two together, you get H2 gas, which bubbles out of solution. So sometimes chemists will show it as bracket G and then an up arrow to indicate that it bubbles out of solution. It's a really nice base to use, although it's really strong. Oftentimes people will ask me, why don't we always just use the strongest base possible? What do you guys think?
Bad.
Safety, big one. Another one is you might deprotonate every proton on your molecule because it won't care anymore. So you want to choose the right base for the right job. So for example, if you go down to some of these super heavy duty bases, that N-butyl lithium or lithium diisopropylamine, once you get down into those bad boys, they will actually catch on fire when they're exposed to air. They're not easy to use. They're not easy reagents. In fact, a couple of years ago, a researcher at UCLA accidentally sprayed it all over herself, caught on fire, and then died from a lab accident. So labs more and more do not want you to use the super heavy duty bases. Technically, you're not wrong if you use them, but you're just creating more trouble for yourself than is necessary. So always choose the strongest base you need, but not anything stronger than that. That's good enough. So we'll go up here and we'll say, all right, pKa of hydrogen we said was 36, and we'll plug that in. This means that we're good to go. Does that make sense when you're choosing bases? This is a really helpful handout. I want you guys to hang on to this. It can be a useful study aid. I'll also put it on the class website as well. All right, let's do another one. This is a two-part practice problem. Number one is find the most acidic proton. And then number two is select a base. All right. Yeah, select an appropriate base, not just any base. All right, and I've got this compound right here. So we have to determine which proton on this compound is most acidic. And then if we want to deprotonate that proton, what base should we pick?
Isn't that anhydride?
It's not an anhydride. If it were an anhydride, we'd have to have an oxygen right there, but close.
Some kind of a
This is a diketone, meaning two ketones that are next to each other. Also give you guys another hint for this one. This was, actually, let's wait. I want us to pick the right proton first, and then I'll tell you the pKa.
I'm gonna go with what you said this time.
I'll draw in all the protons just for fun. Raise your hand if you think you've identified the most acidic proton. All right, let's think about this. If we pull the red proton off, negative charge will be on a carbon. Pull the blue proton off, negative charge is on a carbon. Green proton off, negative charge on a carbon. So we're tied. We have to move down the list. We have to look at resonance now. If we pull a red proton off, is there resonance?
Yes.
Yes. If we pull a blue proton off, is there resonance?
Yes.
Yes. In fact, if there's a line of symmetry down the center of the molecule, they're very similar. What about that green proton? Is there resonance?
What? More.
Ah, there's more resonance for these green protons, right? If you think about this and we pull off one of these guys, we now have a negative charge. This negative charge can delocalize either up to this oxygen or it can delocalize up to that oxygen. So it's got a lot more resonance stabilization because that negative charge can be delocalized across two oxygens as opposed to only one. All right? So let's erase this really quick. We'll write most acidic due to resonance. Across two oxygens. All right, the pKa of this one is about 9. Let's pick a good base to deprotonate one of those green protons. We don't want to accidentally deprotonate one of the red or blue protons, though, just one of the green ones.
Potassium carbonate.
Calcium carbonate.
Potassium.
Oh, potassium carbonate. All right. Does anybody think we should maybe use something with a little bit more gusto? We could use lithium diisopropylamine. That might be overkill. Oftentimes when we're trying to find a good base to use, let's go up and look at this table. A good rule of thumb is the reaction will go to completion if there's a pKa difference of about 5 or greater. If it's only a difference of 1, you might actually be battling that equilibrium a little bit. So you are correct. The equilibrium would favor the product side, but we would still have a little bit of the starting materials left. So knowing that, what might be a better base to choose?
Sodium hydroxide.
Ah, sodium hydroxide. So let's make a note here. Good idea to pick a base where conjugate acid is 5 or more pKa units larger. Yeah, exactly. If it's 5 orders of magnitude less acidic, you know that's definitely going to drive the equilibrium to the other side. As opposed to 1 order of magnitude, you might have 10% still sitting at that starting material side. All right, I think that's where we're going to leave off today. Tomorrow when we come in, we're still going to use this handout, so don't leave it at home. We're going to look at the other side, which is the common solvents in organic chemistry, and we're going to try to pick an appropriate solvent for our acid-base reactions.